Hey everyone, welcome back to the lab. As your instructor for MST613, I'm super excited to get you prepped for your upcoming practical assessment. We're going to run through a rapid-fire 5-minute study guide explainer right now. We've got a lot of ground to cover, but I promise, by the end of this session, you're going to have this material down cold.
Right off the bat, let's do our 10-second brief. If you remember absolutely nothing else today, lock this in. X-rays are electromagnetic radiation, and they uniquely behave as both waves and particles. For our purposes, they're defined purely by two interrelated things: their wavelength, which we call lambda, and their energy, E. Just keep those two variables in the back of your mind.
Okay, here's our game plan for this session. We'll quickly cover how X-rays are actually generated, check out the physical anatomy of the tubes, break down the core math, talk about choosing the right anode materials, run through a quick pop quiz to test your instincts, and then finish up with how this is used in the real world.
All right, let's jump straight into the physics of how we actually make these powerful rays.
So inside a vacuum, we have a heated filament acting as our cathode, and it's basically boiling off electrons. We take those electrons and violently accelerate them across a gap using a massive voltage. When they smash into the pure metal anode target on the other side, all that kinetic energy has to go somewhere. It's conserved and released as X-ray photons. Honestly, it's pretty much a high-speed subatomic car crash that spits out invisible light. Now, taking a step back, let's look at the actual physical machinery you'll be handling in the lab.
The thing you have to understand is that generating X-rays is incredibly inefficient. A huge chunk of the energy from those electron collisions just turns into pure, intense heat. See those cooling water lines pumped directly into the head right behind the anode? Without that constant flow of water, our metal target would literally melt in seconds. Plus, the whole thing is encased in a massive aluminum shielding tower. That's an absolute non-negotiable safety feature to stop scattered radiation from escaping and, harming the operator, which is us.
Okay, so we've got our X-rays. Let's talk about the math that actually governs them.
I know, no one loves equations, but this one is actually really elegant. The energy of the X-ray equals Planck's constant times the speed of light, all divided by the wavelength. But since we're in the lab, we just substitute the constants to get our incredibly practical formula: energy equals 12.398 divided by lambda. The absolute key takeaway here is the inverse relationship. As you crank up the energy of those electrons, your resulting X-ray wavelength gets shorter and tighter. High energy equals short waves.
Moving right along, let's get into the setup phase, specifically how you choose your anode material, because this will literally make or break your experiment.
Different pure metals produce different characteristic wavelengths, so consider this your ultimate lab cheat sheet. Copper, sitting there at atomic number 29, that's your everyday workhorse, perfect for general inorganics. But say you're looking at organics with big atomic spacings, you're going to want the longer wavelength of chromium. On the flip side, if you're analyzing tiny unit cells, like tight metal alloys, you need the heavy hitter, molybdenum, running at 80 kilovolts for those super short, penetrating waves. You always have to match your anode to your sample to avoid throwing off your data.
All right, let's see if you guys were paying attention. Time for our rapid-fire pop quiz.
Scenario 1. You've got an iron-rich sample, and you know iron fluorescence is going to totally wash out your detector. What's your go-to anode? Lock it in. You're going to want an iron or cobalt anode. Using those entirely bypasses the fluorescence problem.
Next up, you're analyzing a standard, run-of-the-mill, inorganic ceramic. What's your best overall anode to reach for? Think back to our syntax systems. Yep, copper is your absolute best friend here. Question 3, let's pivot. You bring in an organic polymer with very large atomic d-spacings. Which anode gives you the high resolution you desperately need? The answer is chromium. That longer wavelength is absolutely perfect for measuring wide gaps. Okay, question 4. You're deep into metallurgy now, looking at a dense metal alloy with tiny, tightly packed unit cells. What do you need? You'll want that short wavelength, high-power molybdenum at 80 kilovolts. Last one, and it's a bit of a trick question about drawbacks. Which anode comes with the specific disadvantage of strongly fluorescing chromium if it happens to be in your sample? If you remembered iron, awesome job. You always have to anticipate what secondary radiation your anode is going to trigger in the specimen.
So why does all this generation math and material selection matter outside this lab?
Well, out in the real world, we use X-ray photoelectron spectroscopy, or XPS, to solve some pretty massive industrial problems. We're talking defect analysis to figure out why paint is peeling off new cars. We use it to find microscopic surface contamination on construction steel before it leads to a catastrophic failure. We even use it in healthcare to analyze how advanced wound dressings interact with biology. None of these life-saving and industry-building checks are possible without the foundational generation principles we just covered.
And that pretty much wraps up our study guide session. You guys now know how X-rays function as both particles and waves, how we generate them, the critical safety systems keeping us alive, the math behind their energy, and exactly how to pick your anodes. You are totally locked and loaded. So, as you head into your practical exam, I want you to think about this. Armed with this incredible tool, what structural secrets of a mystery material are you going to uncover next? Good luck studying, everyone, and I'll see you at the benches.